This is our final lecture on general tensors required for the study of general relativity. And in today's lecture, we are going to see two very important tensors which are vividly used in general relativity. And these are actually a Ricci tensor and Einstein tensor. Okay. In fact, both of these tensors find a vivid application while studying the general relativity. In fact, after knowing about these two tensors, it will be very easier to understand the theory of general relativity. Okay. So one by one, we will learn about both of these tensors. First of all, you should note that both of these tensors are obtained by the process of contraction. And you know how a given tensor is contracted because I have already provided video on the contraction process previously. Okay. So by the process of contraction of a particular tensor or particular identity, you will see we will obtain these two tensors. So first of all, I am going to talk about Ricci tensor. In fact, this Ricci tensor is obtained by the contraction of Riemann tensor, or you can say Riemann Curvature tensor or the Riemann Christoffel tensor. In fact, when this Riemann Curvature tensor is contracted, then we obtain a tensor of rank 2 which is called Ricci tensor. So if you write the Riemann tensor in this form, this is the covariant form of Riemann tensor R lambda mu nu sigma. And if you will take the inner product of this Riemann tensor R with the fundamental tensor G superscript lambda sigma, then you know when we take the inner product, what will be the result. Actually, while taking the inner product with this fundamental tensor, it means you are going to contract this tensor R with respect to the indices lambda and sigma. So lambda and sigma will now cancelled and your final result will be simply R mu nu. And this tensor R mu nu, which is actually a tensor of rank 2, this is called Ricci tensor. Okay. You can also find this Ricci tensor by the process of contraction in another manner. You can see if you want to find this tensor R mu nu, you have to contract this R superscript lambda mu nu sigma with respect to lambda and sigma, as I have told you here. Okay, I have actually taken here the mixed Riemann tensor. Okay, here we have taken the covariant form of Riemann tensor, but here we are seeing the how the mixed Riemann tensor will be contracted with respect to lambda and sigma, and that will be resulted into the Ricci tensor. So if you are going to contract this tensor R with respect to the indices lambda and sigma, then we will actually write lambda instead of sigma or sigma instead of lambda. And you know the process of contraction that will be actually omitted, and so finally we get this tensor R mu nu. Okay. So in this way you can easily say that when we take a Riemann tensor and we consider the contraction of Riemann tensor with respect to two indices, then we get simply the Ricci tensor. Okay. Now in fact, this Ricci tensor is a symmetric tensor, and you can easily prove its symmetry property. You know that this R mu nu can be written as the inner product of the fundamental tensor G lambda sigma times R lambda mu nu sigma. Okay, and as you have studied earlier that the Riemann tensor is actually symmetric with respect to the pair of indices. The first pair is lambda mu, second pair is nu sigma. And if you will interchange without changing the order, then the tensor remains same. You have studied earlier. So using this symmetry property of Riemann tensor, instead of this R lambda mu nu sigma, you can write R nu sigma lambda mu. Now when you will take its inner product with G lambda sigma, it means you are contracting now this tensor with respect to the indices lambda and sigma. So lambda and sigma will get omitted and the remaining tensor will be R nu mu. So how easily we have proved that R mu nu is equal to R nu mu, and that's why we simply say that Ricci tensor is a symmetric tensor. Okay. Now there is also a very important property of this Ricci tensor. If one try to find the contracted value of this R mu nu, what will be that? It means if you contract this Ricci tensor further, then actually after the contraction of Ricci tensor, we get simply a scalar or an invariant which is called actually curvature scalar, and it is denoted by R. Okay. So this curvature scalar R is defined as the contracted value of this Ricci tensor R mu nu, and for it you have to take the inner product of this R mu nu with this fundamental tensor G superscript mu nu. You can see that this, when you will take both of the indices, will get omitted. Okay, and the remaining quantity will be R, which is actually a tensor of 0 rank, and this is a very important tensor which is called curvature scalar or curvature invariant. Okay, so this is all about the Ricci tensor. Okay, now the another tensor which we will see today is Einstein tensor. This is actually the most important tensor, because when we will study the Einstein's theory of gravity in general relativity, the Einstein's field equation is in terms of this very tensor, and that's why this tensor is called Einstein tensor. In fact, this Einstein tensor is also obtained by the process of contraction. But what will be contracted to obtain the Einstein tensor? Actually, it is found that when Bianchi identity is contracted, then we get a tensor which is called Einstein tensor. Okay, you have learnt about this Bianchi identity in my previous video. So let us start with the expression for this Bianchi identity and try to contract it, and finally you will get a tensor which is called Einstein tensor. So for this you have to remember what we have learned in the previous lecture regarding this Bianchi identity. You have seen that this Bianchi identity is defined like this. This is the covariant derivative of the Riemann tensor lambda mu nu sigma with respect to rho, plus the covariant derivative of the Riemann tensor lambda mu sigma rho with respect to nu, and plus the covariant derivative of Riemann tensor lambda mu rho nu with respect to sigma, and sum of these three covariant derivatives of Riemann tensor is equal to 0. Actually, this expression is known as Bianchi identity. And for getting the idea of Einstein tensor, you must remember it. Okay. Now you have seen that this Riemann tensor or mixed Riemann tensor is actually an anti-symmetric tensor with respect to the pair of indices at the place of covariant index. So if we will apply the anti-symmetric property of the Riemann tensor in this second term only, then what will be our result? So if you apply the anti-symmetric property only to this second term, then the first term and the last term will remain at each. But here I am taking the anti-symmetry property with respect to the indices rho, sigma and rho. So when sigma and rho will get interchanged, the sign of this tensor will get changed. So this will be equal to minus r lambda mu rho sigma semicolon nu. Okay. Now we will contract this expression defined in equation 4 with respect to the indices lambda and sigma. So at the place of sigma we will write now lambda. So mark it. In the first term this sigma will be replaced by lambda. I have done it. In the second term again this sigma will be replaced by lambda. Other indices will remain at each. Okay. And in the last term this sigma will be replaced by lambda. Okay. Now this expression can be written like this. This is since here lambda and lambda both are common in the at the place of contravariant index and covariant index, so you know by the process of contraction that it will get omitted, and the first term will be only r mu nu semicolon rho. It means this will be the covariant derivative of the tensor r mu nu with respect to rho. And the second term will be r mu rho semicolon nu. And the third will remain at each, because here this lambda is not a covariant index, but it is the index with respect to which we are going to find the covariant derivative of this last tensor. Okay. So you can write now the first term becomes this, second term is this, and the last term is at each. Okay. You have learnt earlier that the covariant derivative of the fundamental tensors are identically zero. You have seen this fact several times. So taking this very fact under account, this expression can be now written like this. This is g mu rho times r mu nu, and we will take the covariant derivative of this much with respect to rho. Since the covariant derivative of g mu rho will be 0, so this term and this term is equal. Okay. And similarly the second term will be written like this, the third term will be written like this. Okay. Actually the first term represents the covariant derivative of the fellow inside this bracket with respect to rho. The second term represents the covariant derivative of this fellow inside the bracket with respect to nu, and the in third term actually this is the covariant derivative of the term inside the bracket with respect to lambda. Okay. But you know the inner product of this g and this r in first term will be what? You can see mu is common in both in the contravariant index and covariant index, so that will be omitted, and this will be simply the mixed tensor R rho nu and semicolon rho. It means this is the covariant derivative of the mixed tensor R rho nu with respect to rho. Okay, and see this second term. Here both the indices mu and rho are common, so both will be omitted, and therefore this product will be just a scalar or invariant. Okay, so this R is a scalar or invariant which is called curvature scalar. Okay, and we have to take its covariant derivative with respect to nu. Okay, and see now this last term here, mu rho are common indices that will be omitted, so the remaining tensor will be R lambda nu. Okay, and there will be the covariant derivative of this R lambda nu with respect to lambda. So this is our result. Okay, now to write this expression in a proper form, let us change the dummy indices rho and lambda to mu. It means rho will be now changed to mu. Okay, this lambda will be also changed to mu. So instead of rho and lambda in each term, we will now write mu. Okay, so see here, in first term there is rho and that rho will be replaced by mu. Okay, and here there is also rho that will be replaced by mu. Okay, in the second term there is second term will be at each, because here there is no rho or lambda, and in the third term this lambda will be now replaced by mu, and this lambda will be replaced by mu here. Okay, now this, see this first term and the last term both are same, so this will be 2 times R mu nu semicolon mu. Okay, and the second term is at each. Okay, but what is this covariant derivative of the curvature scalar R? R semicolon nu, what does it mean? It means this is the covariant derivative of R with respect to x nu. So this is simply written as del R by del x nu. Okay, and this can be written like this. This is del x mu delta mu nu R. Actually here you know this delta mu nu, this is actually the Kronecker delta, you know it. This is Kronecker delta. And what is the property of Kronecker delta? This is equal to 1 if mu is equal to nu, and this will be 0 if mu is not equal to nu. So when you will take mu not equal to nu, then this term will be 0, but when you will take mu is equal to nu, then here there will be nu and this Kronecker delta will be 1, so our term will be simply this del R by del x nu. So instead of del R by del x nu, we can easily write this. Okay, so this is just the covariant derivative of the inner product of this curvature scalar R and the Kronecker delta. Okay, so symbolically now you can write this derivative in this form. This is the covariant derivative of delta mu nu times R with respect to mu. Okay, so now at the place of this second term in our this expression, we can write this much. Okay, here in this expression. So now equation 5 will become like this. The first term is at each, you can see, and at the place of second term I have written this much. Okay, now take this mu as 2 as a common factor. When 2 will be taken as a common factor and 2 will be when 0 will be divided by 2, the result will be 0. So at the place of first term you will have R mu nu semicolon mu. and at the place of second term there will be 1 over 2 delta mu nu times r. Okay, since both are differentiated here with respect to mu, so you can write now this is the covariant derivative of r mu nu minus half delta mu nu r. Okay, so this last expression actually represents the covariant derivative of the fellow inside this bracket with respect to mu. Okay, in fact this fellow inside the bracket is denoted by the symbol g mu nu. G mu nu, this is for this. Okay, and therefore the covariant derivative of this g mu nu is equal to 0. Actually this is also a very important equation in general relativity. When we will discuss Einstein's field equation, then you will see this equation there. Okay, in fact this result which I have finally obtained in this equation A for the tensor g mu nu, which is defined like this. This very tensor is called Einstein's tensor. Actually this is the mixed Einstein tensor because here there is both contravariant index and covariant index. Okay, so this is the defining equation of the mixed Einstein tensor. But we can also obtain the covariant and the contravariant form of this Einstein tensor. How we can obtain this? Let us see. First of all, we are going to see the covariant form of Einstein tensor. For obtaining the covariant form of Einstein tensor, let us see. If you want to write a covariant tensor, let us say this g lambda nu. This can be written as the inner product of this mixed tensor g mu nu and the covariant fundamental tensor g lambda mu. You can see the index mu is common, so that will get eliminated, and the this will be actually simply g lambda nu. Okay, and therefore we can write like this. Now you have just seen that this mixed tensor g mu nu, which is called mixed Einstein tensor, is defined by this expression. Okay, here actually in this first term is the mixed Ricci tensor and R is the curvature scalar. Okay, now when you will take the inner product of this mixed tensor R mu nu with this fundamental tensor g lambda mu, what will be your result? You can see the common index mu will be omitted and our result will be R lambda nu. Okay, here there is lambda, here there is nu, and in the second term again mu will get omitted and this will be actually equal to g lambda nu, g lambda nu times R. But you can freely change this dummy index lambda. So if now in this expression we write mu instead of lambda, it means lambda is now replaced by mu, because our aim is to write the Einstein tensor in terms of the indices mu and nu. So lambda has been replaced, okay, by mu. So replacing lambda by mu, our result will be g mu nu equal to R mu nu minus this much. Okay, this is actually the covariant form of Einstein tensor. This g mu nu is covariant Einstein tensor. Okay, again R mu nu is the covariant Ricci tensor and g mu nu is the covariant fundamental tensor and R is curvature scalar. Okay, in the similar manner you can also obtain the contravariant form of Einstein tensor. Okay, And for this, let us start to define this tensor G lambda mu. This you can see, this is just a second order contravariant tensor. Okay, and you know this tensor can be equated to the inner product of this mixed tensor G mu nu with the fundamental tensor small g lambda nu. Here nu is common indices and that will be omitted, and your result will be simply g lambda mu. Okay, but we have seen the expression for this mixed Einstein tensor, which is this much. Okay, now take the inner product of the first term and the second term with this fundamental tensor g lambda nu. You can easily recognize here that the product of this g and this r mu nu will be simply equal to r superscript lambda mu. Okay, and the product of this g and this Kronecker delta will be equal to this g lambda mu. Okay, now you can replace this mu by nu. Okay, and mu by nu, yes, and lambda by mu. Okay, so after replacing lambda by mu and mu by nu, our result will be like this. This is this contravariant tensor g mu nu equal to this much. Okay, so all these three equations A, B, C defines the Einstein tensor in mixed form, in covariant form, and in contravariant form. All are equivalent to one another. But you can see ultimately this Einstein tensor is just a combination of the Ricci tensor and the scalar curvature via this fundamental tensor. Okay, so these are the different form of Einstein tensor. Now a very important property of Einstein tensor is that the divergence of Einstein tensor is 0, and this fact already we have seen earlier. In fact, you know, if you want to find the divergence of a tensor, then how it can be obtained? If you define the divergence of g mu nu, which is a mixed tensor, then in accordance with the definition of divergence of a tensor, this can be written as the covariant derivative of this tensor g mu nu with respect to mu. But you have already seen earlier in this equation number 7, you can see that the covariant derivative of this tensor g mu nu, which is Einstein tensor, is equal to 0. So we can easily say that the divergence of Einstein tensor vanishes. Okay, or this is identically 0. So in this way we have actually finished the basic idea of the tensor analysis, which will be required for the study of general relativity. And I hope after watching all these videos provided by me in this channel, in this playlist, you will have a concrete idea of tensor analysis, and this will help in your study of physics and mathematics both. And finally, our ultimate aim is to study general relativity, where you will find the utility of these ideas. Okay, so now in our forthcoming videos we will start the Einstein's theory of gravity, that is the general theory of relativity. Okay, thank you very much.